Okay, today we're talking about laws of exponents, and we got a lot to cover in a little amount of time, so let's get moving. Most of this we've discussed in the past, so we'll start off with products of powers. What I'm talking about here is if I have 6x cubed times 2x to the 7th. I know I multiply that 2 and the 6, which gives me 12. But the question is, what is my new exponent here? Well, if you remember, when I multiply monomials, I add the exponents. So 3 plus 7 gives me 10. So my final answer would be 12x to the 10th. Try this next one on your own. We'll have 3y to the 4th times 7y to the 5th. Good, we should have gotten 21y to the 9th. I also want to talk about powers of powers. Meaning what happens when I have 2 cubed squared to the 4th. That's a lot of powers. And I don't want to know that 2 cubed is 8, and then 8 squared is 64, and then 64 to the 4th. Like, that's a lot of work. So how can I manage my exponents so I have 2 to the somethingth? Well, when I have powers of powers, I need to multiply the powers. So I'm going to end up multiplying 3 times 2 times 4. Well, 3 times 2 is 6, times 4 is 24. So I have 2 to the 24th power, which is going to be a really, really big number. But let's try another example on our own here. What if I just have 2 squared to the 4th? Try that one. Good, we should have gotten 2 to the 16th power. Finally, when I'm talking about powers and products and all that kind of stuff, what about powers of products? We did products of powers, but what about powers of products? So this is when I have 2xy squared and that whole quantity squared. This squared kind of acts like I'm distributing. It's going to go to each piece of this puzzle. So I'm going to have 2 squared, x squared, and then remember when we have squares of squares, so that's y squared squared, we would multiply that. So 2 squared gives me 4, x squared, y to the 4th. Try another example on your own. Let's say I start with 3x squared y, and that quantity is squared. We should end up getting 9x to the 4th y squared. Our next topic is going to be about quotients. Quotients meaning division. So we'll talk about quotients of powers. So let's say I start with g cubed h to the 5th over g to the 1st h squared. How do I come up with just one answer? 1g, 1h kind of thing. Well, when I see that division, I'm going to subtract down the exponents. So I say, to get my g exponent, I say 3 minus 1 is 2, and 5 minus 2 for h is 3. So I have g squared h cubed. Try this example on your own. X cubed y to the 4th over x squared y. You should have remembered that this y has an exponent of 1, which means when I subtract down, I get x y cubed. We did quotients of powers. Let's try powers of quotients. So this is when I have maybe 3p cubed over 7, and that whole quantity is squared. Again, this acts like the distributive property, each piece of the puzzle. So I have 3 squared p cubed squared over 7 squared, which will end up giving me 9 p to the 6 over 49. If I can reduce, I should. This one I cannot. Try this example on your own. 3x to the 4th over 4, quantity cubed. Quantity cubed. We should have gotten 27 x to the 12th over 64. When we're talking about quotients, this also kind of brings into the topic negative exponents. And negative exponents tend to scare people. They can be a little tricky. So let's play with them. So I have n to the negative 5th, p to the 4th, r to the negative 2. Anything that's in a negative should go, like if I have a negative in my numerator, I put it into the denominator and it becomes positive. So I can move it to the other side of the division or the fraction side and it becomes a positive. Likewise, this r squared, or r to the negative 2 in the denominator, if I move it to the numerator, it now becomes positive. So when I switch those two things, I would get r squared p to the 4th over n to the 5th. And that way everything is positive and pretty. We don't like negatives in our exponents, so we try to move them around so it looks nice. So this example, and we'll work it together, kind of combines a couple things we've been learning. So we'll start with a to the 5th, b squared, c, over a to the 7th, b squared, c cubed. So let's go ahead and apply the fact that we know quotients of powers, where we subtract the exponents down. My a's, 5 minus 7, would give me negative 2. 2 minus 2 is 0. And this is a 1. 1 minus 3 is, again, negative 2. So now we can apply that negative exponents thing. If I move a and c into the denominator, they become positive. So I have b to the 0 over a squared c squared. The key thing to remember, however, and maybe we remember it from years past, is that anything to the 0th power is what? Good, it should be 1. Anything to the 0th power is 1. So this really simplifies down even further to 1 over a squared c squared. Our last bit of thing, and this might be the newest stuff, is rational exponents. So for example, if I have 25 to the 1/2 power, 1/2 just means that I put it in a square root, where this is a 2 out front. Normally with a square root sign, we don't write that 2. If the base here changes, the denominator, we will change this. So the square root of 25 we know to be 5. And we can write that vice versa, 2. If I take the square root of 18, that's the same thing as writing 18 to the 1/2 power. Okay? Remember how I said the denominator could change? That's where we talk about nth roots. Okay? So let's say I have the cube root of 27. Did you know we could take the cube root? We can. So when I say nth roots and the cube root and all that, it doesn't have to be the cube root. It could be the 5th root or 4th root or whatever. But we'll say n cubed is equal to 27. because really 5 squared was equal to 25, and that's how we got this mess up here. So n cubed is 27. What is n? Well, we know 3 squared, or 3 cubed is 27, so n must be 3, and that's how we took the nth root. So we'll try it. I'll let you try it with this example. The 5th root of 32. What do I multiply together 5 times to get 32? If we're working it out, we should get that n equals 2. So what this really means for us is that for any base b, we can do it with 1 over n, where n is any integer. So if I have 125 to the 1/3, I can solve that. That is the cube root of 125, which gives us 5. Try this next one on your own. That should be the cube root of 27, which is 3. Not only can I do b to the 1 over n, I can also do it to any fraction, m over n. And how that kind of works is, let's say I have 64 to the 2/3. What I'm looking for is that denominator tells me what root I'm taking. So I'm taking the cube root of 64. And then the numerator tells me I'm going to square whatever that answer is. So I know that the cube root of 64 is 4. And I'm now going to square 4, which would give me 16. Okay? You won't see a ton like this, but you will see a few. We can also solve for exponents. So let's say I start with 5 to the x equals 125. I just want to know what that x equals. 5 to the what power gives me 125? Well, if you remember back a few examples, we know that the cube root of 125 is 5, so x here must be equal to 3. That one was pretty easy. But what if they give us one where it's 25 to the x minus 1 power equals 5? How on earth would I begin to solve this? Well, let's break down 25 so I get the same base on both sides. I know that 25 could be expressed as 5 squared. And I still have that x minus 1 power hanging out up top. And this is really 5 to the 1st. If I have the same base, I can set the exponents equal to each other. So I can have 2 times x minus 1 equals 1. From here I distribute. So I have 2x minus 2 equals 1. I add 2 to both sides. When I add 2 to both sides, these cancel. I get 2x equals 3. I divide both sides by 2. And I get x equals 3/2. If I went back and plugged that in to check, here's my original equation way up here, that would be 25 to the 3/2 minus 1. 3/2 minus 1 is really 1/2. 25 to the 1/2 means I take the square root of 25, which we know to be 5. And hey, that's the answer I wanted originally. Thanks for watching.